Good afternoon, everyone. Thank you for coming out. I'm Nicola. This here is Anne, and together with Norbert and Johan, we've been working on this project for the past year and a half. We've been working very closely with our consultants, Dr. Michael Pope and Dr. Leonardo Simone, and we'd like to say a special thank you to Canadian General Tower, or CGT, who's been helping us along the way as well. So, synthetic leather car seats are even more common than real leather car seats. Now, the major problem with leather or synthetic leather is that they get uncomfortably hot in the sun and uncomfortably cold in the winter. And especially in our climate, where the temperature is constantly changing, this is a continuous problem. It requires large amounts of energy in cooling the seats or in heating the seats to make them more comfortable. So some of the major pros of having synthetic leather is the haptics. They feel very nice to the touch, and they feel like real leather. They're also affordable, more durable, stain resistant, and they're aesthetically pleasing. But again, the temperature control is terrible. So the market. It's a huge market. Like, there's an expected value of $18.45 billion by 2019. So it's a good time to be trying to introduce a new product into this market. Especially in electric vehicles, when you're using your battery to power how far your car goes, if you're expending all of this energy on cooling your seats, you're directly taking away how far that vehicle can travel. So if we can find an energy-free solution to cooling your seats and making it more comfortable, this has a very direct impact on this market. So microencapsulated phase change materials, or MEPCMs, are a commercially available product that can be used to modify the temperature and moderate it at a specific temperature in a matrix. It is simply a paraffin wax on the inside, similar to that of a candle, and it's encapsulated in a thermopolymer shell. Now, this wax has a very high latent heat storage, and what that means is that as there is thermal energy from outside, it is able to absorb a large amount of this thermal energy, store it in the wax, and use it to change phase from solid to liquid. And this is how it's able to pull the temperature and the thermal energy out of its surrounding matrix and is able to stabilize the temperature at its melting temperature. They're also inert, non-toxic, and non-corrosive. One of the best parts about MEPCMs is the fact that you can tune their melting temperature and thus the stabilization temperature. Simply by adding an extra carbon in the chain, you can increase the melting temperature of the material, which means you can also increase the stabilization temperature. So our solution is to add these MEPCMs into a synthetic leather to achieve an energy-free solution to the temperature maintenance in your car seats. So this is a schematic of our design, and we're going to start at the bottom, working our way up. There's the foam that is stretched over your foam car seat. There's a fabric layer and a polyvinyl chloride foam. This is followed by the PVC film, and this is where we wish to incorporate the MEPCMs into. It's a 200 micron thick layer, and we've chosen this layer to integrate our MEPCMs into as it is very close to the body. The PU coating is only a couple of microns thick and is simply used as a finish. So it's close to the body. It's also a solid layer. This means that it's in full contact with the MEPCMs throughout to be able to draw that thermal energy into the materials. So we've designed this for our customers, and we've looked at some of the data that MasterCard performed on a study to see how many times people go to the grocery store. And it's typically about 3 times a week. 1 for a rather long shopping trip to stock up for the week, and 2 more, those quick shopping trips when you've forgotten something. And those typically last about 18 minutes. So for our proof of concept, this is the target. We've decided to maintain the seat temperature at about 34 degrees Celsius. Now, we've chosen 34 degrees Celsius as its skin temperature. Everybody has their preference for how hot or how cold they like it. how cold your hands are. So we've chosen 34 degrees because it's a standard of people's body temperature, and it will feel either hot or cold relative to that temperature. We also wanted to make sure that we were retaining the haptics, or how they felt. If we're adding capsules into that top layer, we wanted to make sure you couldn't feel the bumps in that material, because then people would not want to purchase that material. Secondly, we wanted to be able to maintain the mechanical integrity of the material, because they're being used on seats. People sit on them, they throw their bags on them. They need to be able to withstand some of that mechanical integrity. So we wanted to make sure that we evaluated that in our material. Finally, we wanted to make sure it was integratable into existing infrastructure. It was much more adoptable if it's able to use the existing infrastructure. So we started with our design in a model of COMSOL, and we used a thermal model to be able to design our material. So we used a 1 meter long PVC film, and we exposed this to a changing ambient temperature, increasing over time. We could definitely see that there was a stabilization at the melting temperature of our MEPCMs. Eventually, when you reach the liquid stage of the MEPCMs, then it will increase the temperature to meet the PVC. So fabrication was performed at CGT's facilities using their lab scale equipment. First, all of the components were mixed in with the mill, and this uses the shear stress and pressure and temperature in order to mix the components of the PVC. This is where we were able to incorporate our MEPCMs into the infrastructure. We then put this film on a calendar, which makes the 200 micron thickness, and we then can run it through an embosser. And what this embosser does is it uses heat and pressure on a roll, and it inserts all the veins that look like leather onto this material.
We were able to receive a variety of samples of MEPCMs that were commercially available from BASF. Unfortunately, BASF uses MEPCMs that are applied for building applications, specifically to help moderate for HVAC purposes. So the majority of MEPCMs we received ranged from 23 to 28 degrees Celsius. Once they were received, we wanted to ensure that the melting temperature of the MEPCMs corresponded correctly to the actual melting temperature of the material. So we used DSC to actually analyze the melting temperatures, and you can see the different melting points of the paraffin wax inside. So it did correspond well with the technical data sheets. We also wanted to cycle the MEPCMs up to 200 degrees Celsius to ensure that they would be able to withstand the processing temperatures used at CGT, which they did withstand. Here you can see 2 different dispersions. So of the 5 samples we received, one of them was aqueously dispersed and the other was a solid powder. The aqueously dispersed MEPCMs showed a substantially smaller particle size as well as much more monodisperse. In the solid powder, you can see that the particles are much more variable, ranging anywhere from 50 to 80 microns in size, and they were actually an aggregation of the smaller particles, making them non-optimal for integrating into a 200 micron film in terms of haptics. Here you can see images of the films that we actually had fabricated. So these films were imaged under optical microscopy, and it was when we decided to take a look at the dispersion and determine how consistent it was throughout the PVC matrix. So again, drawing your attention to the large aggregates in the right-hand side image, showing how the PVC had large aggregate pieces of MEPCMs, as well as, in general, larger particles on the whole. We also imaged the cross-section of the MEPCMs in order to determine if there were any surface protrusions. Here on the far right, you can see a large white particle that represents that is one of the large aggregates of MEPCMs, showing possible protrusion through the surface and therefore compromised haptics. We tested the tensile strength of the material as one of our mechanical properties to quantify, and we found that the control outperformed all samples that had MEPCMs integrated into the matrix. However, 30 PHR, or per 100 resin, of aqueously dispersed MEPCMs maintained 77% of the tensile strength, whereas 30 PHR of the solid dispersed MEPCMs maintained only 65%. So there's a 12% difference between the same amount of loading of solid dispersed versus aqueously dispersed MEPCMs. In order to actually test the latent heat storage of our material, we built an enclosure roughly 2 feet by 1 foot by 1 foot. It had an opening on one end, which we used to have a heat lamp send heat through the system, and we used a thermal imaging gun from the top view in order to actually analyze the change in temperature with time. We took the images initially using a rainbow spectrum, so it ranged through the full spectrum of the rainbow, and then we tried to assign RGB values to a specific temperature, but we found that the resolution of the camera wasn't great, and it wasn't completely accurate because of the different RGB values. Each temperature had one set of RGB, and then it was not particularly accurate. So we redid the tests using a grayscale range, which showed much better results because we could directly correlate pixel intensity to the temperature, which was much more accurate. So here you can actually see a video of some of the pictures that we took over time. So as you can see, the temperature increases with an increase in time, and the 4 different samples change in their brightness depending on the sample that they were. The graph on the left here shows a comparison between the solid and the aqueously dispersed samples. So we wanted to justify the aqueously dispersed samples as being equally temperature controlled, but much better mechanical properties, which you can see here given the curves. On the curve on the right, we considered the trend of differences in loading. So what you see here are changes in 20 to 30 to 40 of PHR loading, which substantially improved the temperature control at higher loadings, but also compromised the mechanical properties further. Challenges for the project moving forward would include the commercial availability of MEPCMs. So as I mentioned earlier, we couldn't receive ones at 32 degrees Celsius melting temperature with a PMMA shell, but they can be fabricated and custom made. We also would like to further optimize the temperature testing. So the temperature scale bar across the bottom could be used in grayscale, but we had to fix it in order to make sure that the temperature directly related to the pixel intensity. We decided to go for sensitivity over range, so we fixed our scale bar from 19 to 29 degrees Celsius in order to maintain sensitivity, but testing it at higher temperatures would give you a better idea of how the graph changes with more time and more heat being sent into the system. Pigment addition represented a unique issue at CGT. The introduction of pigment into the system caused some issues, and it seemed to not allow fusing of the material to itself very well, so that would need to be further optimized within the formulation. And the fusing of the materials of the PVC itself at a very high loading would also need to be optimized. So as you went to higher loadings, you lost some of that mechanical strength, so potentially fillers, strengtheners, or other components of the formulation could be optimized in order to still maintain the same mechanical integrity. We did perform a cost analysis in order to determine how much the MEPCMs would cost in order to integrate into the seat itself. So the cost of MEPCMs is $30 per pound, and we found that the seat, we considered the MEPCMs to be integrated only into the headrest, the back of the seat, and the base of the seat. So this roughly worked out to 0.87 meters squared of surface area. At 200 microns thickness, we found that it was only $2.93 extra of cost per seat. Conclusions for the project moving forward would be that we found that aqueously dispersed MEPCMs did perform effectively at 30 PHR by maintaining lower temperatures than the control. We also found that the aqueous samples had a much better dispersion, as can also be evidenced by the samples themselves. We found that the surface protrusions were not observed in the aqueously dispersed MEPCMs, and that the loading at 30 PHR still maintained 77% of the tensile strength. We also found that the addition of MEPCMs can be easily integrated into the existing infrastructure. Recommendations for the project moving forward would be to further optimize the formulation in order to retain the mechanical strength and better incorporate the pigment. We would also like to investigate the incorporation of MEPCMs into the PVC foam layer in order to draw more heat from the surface. Exploring alternate methods of dispersing the solid particles would be quite beneficial because solid particles, you get more quantity per pound, and they're also substantially lighter in general to ship, which reduces your manufacturing costs substantially. And investigating the use of an IR reflective pigment would be a good avenue to pursue reducing the standby temperature of the seat by actually reflecting the sun's rays. Thank you.
So when you mentioned the addition of pigments, what type of pigments are they using usually for this application? Are they organic dyes? Are they silicates of some kind? What type of colors do they exhibit?
So we can't actually disclose the pigments due to an NDA, but they use pigments ranging in a variety of colors. So typically they'll use some sort of black pigment because that's the most common color for car interior, but other colors do exist.
Okay. So the reason I'm asking is there is apparently a compatibility with the pigment incorporation with beads and structures. So I'm wondering, why is that the case? What is the main issue associated with that problem of incorporating it?
There's a lot of components in the PVC formulation. There's lots of different components, and changing those components, stabilizers, dispersants, stuff like that, would be able to better incorporate the pigments. So by changing that formulation, we would be able to get more loading in, hopefully, with some testing. But we worked with a standard formulation to just be able to compare to what's currently used and did not optimize the formulation for the addition of the MEPCMs.
Let me ask you a full disclosure. I happen to know a little bit about CGT and their work with the cool liners and their issues with incorporating pigments in that sort of range of their products. So I'm wondering, how is that different, if you know, with the pigments that are used for car seats application? Are they also solid state pigments?
I'm CGT.
Good. You know Bill O'Keefe then?
Yes.
Good. So they don't have to disclose anything that is I'm not driving it in that way.
No. So I'll just help the students out.
Thank you very much. That would help me too. Yeah.
So just to start off, they did a phenomenal job in coming to CGT and working with the R&D and the product development group. So I'm very pleased that today, and I appreciate you guys for the invitation for allowing us to come here. Thank you. The reason why some of the pigments, there needs to be further formulation work done here is the incompatibilities on the types of plasticizers, all the components that are going into the PVC skin. So you got your plasticizers, you got your dispersants, you got your fillers, and you have to optimize that type of those ratios. You will use inorganics, organic pigments, depending on the materials, and those pigments themselves will have different orientation, and how they balance within the system is what is driving this incompatibility.
Gotcha. But it's not strictly organic or strictly inorganic dyes. You have a mixture. Okay. So that makes it even more difficult